Hey there, Year 12 Method students. In this video, we're looking at 13D, which covers the expected value, the variance, and the standard deviation of a discrete probability distribution. So let's get into it. So let's start with the expected value, which is also known as the mean, or the average, right? So the expected value is the mean or the average, and it's denoted by this symbol here, which we call mu. Kind of looks like a U if it had a little tail at the front. The expected value of a variable x, which can be written as e of x, right? So that's important to understand that e of x is the equivalent of this mu symbol. They both mean the mean or the expected value of our variable, is determined by. So mu equals the sum of x, which is essentially the sum of the possible outcomes that we can have, multiplied by the outcomes probability. Okay, so this notation is potentially a bit confusing, but essentially just means the sum of each x value times by its probability. Okay, and that formula is just the same thing, but with e of x written instead of mu. So in words, e of x is the sum of each possible outcome multiplied by its probability. So it's actually, even though the formula makes it look complicated, it's actually a relatively straightforward process. Let's start with an example where we can maybe kind of think about this using what we know about statistics and the mean, but also then sort of see how it works when we convert things into probabilities. So in this example, we've got Jamie, who's observing the number of people in the cars that drive along her street, and she records the following values for the first 10 cars, right? So she's got 10 numbers here for how many. So the first car, there was one person in it, next car there were 3, next car there were 1, and so on. Calculate the mean of Jamie's data. So we can do that based on what we know the average to be, right? Because we know that if we've got 10 values and we have to find the average, well, we just add them all together and divide by 10. So if we were doing it that way, the way that we've always been used to, it'd just be 1 plus 3 plus 1 plus 2 plus 2 plus 5 plus 4 plus 1 plus 2 plus 1, all divided by 10. All right, and what do they equal? 4, 5, 6, 7, 8, 9, 14, 18, 19, 20, 22. 22 divided by 10, so 2.2 is the mean of those 10 numbers, right? That's how we would find the mean if we just knew the raw data, we knew all the observations. But we can also do this from a probability table. And so let's set this up as a probability distribution and see how we would then have to kind of apply our other formula to find the mean of the data. So based on the observations, well, the possible number of occupants from this information are the numbers from 1 to 5, because we had, obviously there has to be at least one person in the car, and the most that were observed was 5 people. Now, to convert these into probabilities, well, for example, there were 1, 2, 3, 4 cars out of 10 that had 1 passenger in it, and so obviously as a probability we could write that as 4/10 or 2/5, but I'm going to write it as a decimal 0.4. All right. How many times were there 2 people in the car? Well, there were 1, 2, 3 times where we saw 2 people in the car, so that would be 3 out of 10 or 0.3. 3 occupants, that happened once, so that's 1 out of 10 or 0.1. 4 occupants also happened once, so that was 0.1, and 5 occupants happened once as well, 0.1. Okay, so we could do a quick double check that those probabilities add to 1, because remember that in a probability distribution, the sum of all the probabilities should add to 1, and quick check, yes it does. So this is the data recorded, but as probability. So we can think of it as like, well, based on the observations so far, the probability that the next car that drive past would have 1 occupant in it would be 0.4, for example. So if x is the number of people in a car that drives along Jamie's street, use the table to calculate e of x. So we're almost pretending we don't have the original numbers here. We're just going to use the table to calculate the mean. Well, the formula says it's the sum of each x value multiplied by its probability. So it would be, we could say e of x equals 1 times 0.4 plus 2 times 0.3, right? So just taking each x value and multiplying it by its probability, plus 3 times 0.1 plus 4 times 0.1 plus, and the last one is 5 times 0.1. And so, well, what do we get from that? We get 0.4 plus 0.6 plus 0.3 plus 0.4 plus 0.5. So 0.4 plus 0.6, well that's 1, 1.3, 1.7, 2.2. All right, so you can see that this alternative method of calculating the mean from the probabilities as opposed to just from the original numbers has given us the same value, right? We got 2.2 as our mean or expected value. Now, obviously, if you have the original values, it was probably a bit easier to just add them together and divide by 10. But often you'll get questions where you just have the probability distribution. So you just know the possible outcomes and their probabilities, or in other words, the proportion of the time that each outcome actually happens. And so that's when this formula is actually going to be necessary. Just like in the next example. So the next example says, determine the expected value of a random variable which has the following probability distribution. So in this question, we don't even know what the variable represents. We just know we have this variable that can take the possible values or the possible outcomes of this variable can equal 2, 4, 6, 8, or 10. and the probability of each of those outcomes is given in the table. So that's all we have. And so we could say, well, the expected value then, we're just going to go straight to the formula approach, which is to multiply each x value by its probability. So 2 times 0.2 plus 4 times 0.4. In fact, if you understood the previous example, you might want to pause this now and have a go at the rest of the question yourself, but I'll keep going through. So 6 times 0.2 plus 8 times 0.1 plus 10 times 0.1. All right, so 0.4 plus 1.6 plus 1.2, so some good practice with decimal multiplication here. Remember, you just multiply the numbers, and then however many decimal places were in the original multiplication, that's how many have to be in your answer. So plus 1. So what do we get? We get 2, 3.2, 4, 5. The expected value for this one's actually 5. Okay, so that's just a little bit of practice with using that expected value formula. Another good sort of common sense check, like with any time you're ever finding the mean's got to be somewhere between the lowest number and the highest number. So if your possible outcomes are 2, 4, 6, 8, and 10, well, you know straight away that the mean has to be somewhere between 2 and 10. So if you end up with an answer that's bigger than 10 or smaller than 2, that can't really be the mean, right? And you can even look more closely at these probabilities and to sort of build up your estimate and say, well, the probabilities seem to be a little bit higher towards the lower x values, and the probabilities are a bit lower up at this sort of x equals 8 and x equals 10. So you can even sort of estimate that not only will the mean be between 2 and 10, but it might be a little bit closer to 2 than it is to 10. And that is what's going to happen here. So we can always sort of get a good estimate of the mean just by thinking about the numbers before we actually start applying the formula. And that's a good way to sort of preemptively avoid mistakes. Okay. One more sort of practice run here with a worded problem. So in this example, we've got John, who's devised a gambling game based on tossing 3 coins simultaneously. So we're back to the 3 coins example. He charges people $5 to play. If 3 heads or 3 tails are obtained, the player receives $10. Otherwise, the player receives no money. What is the expected gain / loss to the player? And is this game fair? Okay, so what we might do here is if we want to sort of find the expected value, in this case the expected gain or loss, it'd be good to sort of set up a table with the outcomes and their probabilities. So let's try to do that. So let's say, what are the outcomes? Let's let x equal amount of gain / loss to the player. All right, and then we'll set up our table here with x and, well, so we want to keep this as simple as we possibly can. The possible outcomes, well, the possible outcomes that we're really interested in is either that the player wins or loses. Okay, so we're not going to worry about like all the possible outcomes when we toss 3 coins. We don't want to sort of separate into the 8 possible outcomes. What we could say is we could say, well, let's just work out the probability that the player sort of wins. Actually, no, sorry, hang on. What am I doing? I'm letting x equal the amount of gain / loss to the player. Nope, scrap that. So what are my possible values of x? Well, either, so I'm not going to write it as win or loss, that would have not made sense. So rewind that. We're going to say, well, if the player wins, so we're going to think about the player winning. If the player wins, they're going to gain $5, right? Because they've paid $5 to play. And if they win, they get, John's going to give them $10. So they can get $5, right? So x could equal positive 5, okay? Or if they lose, well, if they've been charged $5 to play and then they lose and they just get given no more money, well, then they've really just lost $5, haven't they? So they can also lose $5. So the possible values of x, if x is the amount of gain or loss to the player, are positive 5 and negative 5, okay? And the probability that the player wins and the probability that the player loses, well, that's what we're going to have to work out using our knowledge of this scenario with the 3 coins being tossed simultaneously. And we know that if we're talking about, getting 3 heads or 3 tails, well, the only way that can happen is if we get heads, 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 or tails, 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 okay? And each of those events has a probability of 1/8 of occurring, okay? You can write it out on a tree diagram, but we've done that question with a tree diagram so many times, I can't be bothered doing it again. So if that probability equals 1/8, and this one also equals 1/8, well, then the player has a total probability of 2/8 of winning this game, okay? So 2/8 or 1/4. So the probability that, I'm gonna write as probability that, big X equals little x, well, for the player to win, the probability is 1/8 plus 1/8, which is 1/4. And all the other outcomes result in the player losing. So if we think about our tree diagram, there'd be 8 sort of possible combinations with heads and tails when we toss 3 coins, and 6 of those 8 combinations are resulting in the player losing. So 6 out of 8 or 3/4. Okay, so we've kind of set up the table in the simplest way we can. We've really just thought about the 2 possible values of x, which is that the player can gain $5 or lose $5. Now, you can kind of just tell by intuition that this game is not going to be fair, right? Because the player has, it's an equal amount that they can win or lose, but the probability of them losing is much higher. But let's actually calculate the expected gain / loss to the player. And so we could say, well, E of x equals each x value multiplied by its probability. So plus -5 times 3/4. So we get 5 on 4 minus 15 on 4, which is -10 on 4, which is -5 on 2. Or in the context of this question, when it's about money, that would be like -$2.50, right? Because 5 on 2 is 2.5. So essentially, each time this player plays the game, they're expected to, sort of on average, lose $2.50. Now, of course, sometimes they're going to win, and then probably more times they're going to lose. But overall, if they play the game enough times, on average, they'd be losing $2.50 per game. So no, this game's not fair. So game is not fair. If it was fair, that expected value should be 0, because on average they should win as much money as they lose, and overall it would be fair. So the game is not fair because E of x does not equal 0. That would be the only way for the game to be truly fair, is if the expected value was 0. All right, let's just have a look at this next section. This next section's kind of got a few additional rules, and we've called them expectation theorems, which just means they're like formulas to do with the expected value. And these are usually applied once you know the expected value, and then something kind of changes to the variable. So I'll run you through these. This first one says the expected value of a times x is equal to a times the expected value of x. So if we've got this sort of constant value a here, then having the variable multiplied by a actually is the equivalent of multiplying the expected value by a. The next part says the expected value of a times x plus b equals a times the expected value of x, but then with a plus b at the end. So in other words, if we have this plus b, if we're sort of adding a constant to our variable, well, that's also going to do the job of adding a constant to the expected value. This last bit says the expected value of b is just equal to b. So if it's not actually a variable that you're finding the expected value of, it's just a constant, well then the expected value of that constant will be itself. And the expected value of x plus y, so if x and y are both two separate random variables, well, adding the variables together is the equivalent of adding their expected values together, I guess is what that formula there is saying. Now with a couple of these, they look a little bit confusing, but one way to think of it, as a kind of basic aside here, and I'll try to do this quickly, is that if you had, say if you had let's keep it simple. If you had a variable that just had 3 results, right, 8, 10, and 12. So the expected value of those would be 10. Right, the mean of those 3 numbers would be 10. If we were to take those numbers and let's just say add 1 to each number, right? Well, I get 9, 11, 13. And what would happen to the expected value? Well, the expected value just went up by 1. So the expected value is now 11. Now that makes sense, right? So all that's saying is that if you take the variable and sort of add 1 to everything within that variable, well, then you're also going to increase the expected value by 1. If you multiply by a number, so let's say that we took these numbers and actually we multiplied them all by 2, well, we would expect that that was not an intentional pun, but the expected value is going to double as well, because these numbers are going to become 16, 20, and 24, and the average of those is 20, right? So that's what a couple of those sort of expected value theorems are saying, that if you sort of add a constant to your variable, well, that's just going to increase the expected value by whatever the constant is. And if you multiply your variable, well, you're just going to be multiplying the expected value by whatever it was, whatever that multiplying number was. Okay, so that's kind of a simple example with just 3 basic numbers. But typically when we apply these just as a sort of straight formula. So in this question, we're saying we've got a discrete random variable or variables x and y, and we know that the expected value of x is 2.4, the expected value of y is 3.2. Calculate the expected value of 2x. So that is essentially just going to do the job of multiplying every value in the x distribution by 2, and so that will just have the effect of giving us 2 times the original expected value. Right, that's just applying this top formula. Right, you can see a in this case is 2, so the 2's come out the front here. So 2 times the expected value of x, which was 2.4. So 2 times 2.4, which equals 4.8. Okay, expected value of 3y plus 1. So this one's going to be using that second rule there, where that will equal 3 times the expected value of y. So the fact that we're multiplying the variable by 3 is also going to multiply the mean by 3. But we're also adding 1 to our variable, so that's going to have the effect of adding 1 to the expected value. Okay, so that's how we can kind of rewrite it. And then it's just a case of saying, well, the expected value of y was 3.2, so this is 3 times 3.2 plus 1. So what's that going to give me? That's going to give me 9.6, so 10.6. Okay, expected value of 4x minus 3. Well, this is really similar to part B, but just practice with another group of numbers, so that will equal 4 times the expected value of x minus 3. So 4 times 2.4 minus 3. Oh, now I'm going to muck this up doing it in my head, I reckon. 4 2s are 8. 4 2s are 1.6, so that's 9.6. 9.6 take away 3 gives me 6.6. You can check that on the calculator and make sure I haven't stuffed that up. And lastly, the expected value of x plus y. Well, by this last rule, this just says that that is the expected value of x plus the expected value of y. And so that will equal what we're given in the question, 2.4 plus 3.2, and that'll give us 5.6. All right, so we've got a bit more to cover in this section, but it's a pretty long video already, so I'll pause that there and I'll do the second half of this exercise in another video. But I hope that so far the expected value stuff is making sense for you. Cheers.